surgical device for real-time measurement of hernia defect and other anatomical geometries, presented by Dr. Ivan George.
Great. I want to thank our chairs here, Dr. Clemens, Dr. Herron, and SAGES for allowing us to present our work. I'd also like to acknowledge Dr. Adrian Park and Dr. Gyusung Lee for being co-inventors on this device that we're going to present. Left or right mouse? Just any.
What is the Mac? This is the Macintosh mouse.
So this one just pushing it goes?
Left button, yeah.
Gotcha. All right. So we have no disclosures relevant to this to show. Essentially, I won't get into herniorrhaphy too much here. It's not really the aim of this, but in attempting to measure hernia defect and thinking about it, we were basically saying, how could we measure hernia defects in a more accurate fashion than we had in the past? And we also recognize that measurement of the hernia defect is key to a successful hernia repair. And so we wanted to do it from an indirect fashion. And so let me go over 3 different means that people have tried in the past to do it. Now, those of you that are surgeons or have seen this, all of you should be aware of the analog linear means. So you're taking a ruler and you're kind of putting it up to the defect and you're attempting to make a measurement. Typically, there are some drawbacks to this. It's not that precise, and if you're trying to do measurements of an irregular geometry, not just linear but around the defect, it's not the most efficient way to do that. Also, the next method we've seen used is structured light. Structured light, sort of, for those of you that are not familiar with that, sometimes we call it laser striping. It's very much like the laser system you see at the checkout counters when you're scanning your barcodes. In some instances, you can scan a volume and create an identical computer model of that volume, but the environment doesn't lend very well to it. And then there's videometric, which some of the computer scientists in the room might take some exception, but there's a concept of computer vision, and it turns out that the concept of understanding a dynamic image or scene and then making interpretations from the characteristics of that scene, including measurements, it's not very robust right now, and there's still a lot of cost and effort behind making that happen. So our solution is actually kind of simple. We look to take basic technologies off the shelf and incorporate them into a system that we've actually moved to patent, and it consists of 4 basic parts: a tracking system, and a sensor, and an instrument probe, and a tracking array. So essentially, you have your computer connected to 2 sensors. The sensors can detect where the probe is in space. Basically, we put a tracking array at the external extracorporeal end of the probe or instrument, and then at the distal tip, we're able to select specific points, or we're able to track a series of points. So for our pilot project, we used 2 different types of tracking technologies. The first one was the optical tracking. What you're looking at here is a motion tracking system from Vicon, and this is an instrument that we put together with 3 tracking markers, our tracking array that's on the extracorporeal side. We know the specific measurement, size, geometry of the instrument, so by tracking the external component, the extracorporeal component, we know exactly where the tip is in space. We also used a second method, tried a different tracking methodology. This is a DC active magnetic tracking system, and this was another probe that we had. Now in this case, we can track both the proximal or distal end of the instrument. And sort of on a first pilot, arbitrarily, we created this diagram that you see here, a piece of paper, and there were these line segments, and then this oval and this star, and essentially we threw it into a laparoscopic trainer box, put it in the box, and then we had someone take our instrument, put it through the trainer, and literally pick the 2 points. So the first time they were told to pick the 2 ends, the 2 points, and then our system calculated the distances. And then we also had the individual, the user, simply swipe around, basically paint the edge of the star in the oval. So looking at the linear measurements, this is what we came up with. Those line segments that you saw before, these were the actual lengths in millimeters. These are the trials using the optical system and the electromagnetic system. I mean, we did more than this, but for your purposes, you'll see there's strong correlation between the actual measurement and the measurements we were able to achieve with both systems. In terms of the oval, you'll see this is the optical system on the left, the electromagnetic system on the right. And if you had, to avoid bringing video, we didn't show it, but the top two are 3D representations. So on our screen, you could see it, turn it in whatever way that you, whatever fashion that you wanted. But they were, again, correlated very well. Same is true with the star. And then, knowing that we might apply this to things other than ventral herniorrhaphy, we actually pulled out a triangular block made out of wood and a hand of a mannequin. Truly arbitrary here. And then we had our user paint across it with the instrument tip. Again, imprecisely, they sat there and just drug across it, but you'll see again, optical system on the left, electromagnetic system on the right, and again, these were fully interactive on the screen in real time as we move them around. So there's some pros and cons to both of these tracking systems. With IR, I would, infrared optical tracking, I would only say that one of the concerns we had, and it didn't affect us, and we don't believe it will cause a long-term problem, but it's a line of sight system. So if something gets between your instrument and tracking array and your sensors, it can obstruct and you'll lose the point for that moment. In terms of our electromagnetic commotion tracker, there's really two things to consider. One is that it does have issues with ferrous magnetic metal in the environment. However, these systems have gotten much better and are able to compensate for the metal in the environment prior to its use. And they have limited measurement volume, but again, for the purpose of what we were measuring, it was well within the constraints of where we were looking. You'll see 2 feet, 2 feet, 2 feet. Kind of our next steps and where we're headed right now is that we're investigating other systems, use of accelerometers, gyroscopic systems, RF systems. We've been developing hardware-based computational modules that essentially can basically help us translate the shape to a piece of mesh and basically create exemplars that match up with what's inside the abdomen. And basically we're looking at other opportunities as we move towards commercialization. This can be used for cadaveric use, for research, for a number of different areas, both open and closed. And I want to thank you.